So we're going to take the antiderivative of t times arctan of t, and it's going to be an integration by parts, which means we got to choose a u and we got to choose a dv. And first thought might be to have t be u, because that's a pretty typical choice for us. But that would leave arctan of t for our dv, and that's not a trivial antiderivative. In fact, it takes integration by parts just to find that antiderivative, which I had done in another video if you want to see it, but we're not going to do it here because we don't need to. We're going to switch it up from what we would normally think, and the arctan of t is going to be our u, and our dv then is t dt. That does make for nice du and v, because our du is just 1 over 1 plus t squared, and our v is t squared over 2. So initially setting this up isn't too bad at all. So we have t squared over 2 times arctan of t minus the integral of v du, which is t squared over 2 times 1 over 1 plus t squared dt. Now I'm going to clean this up just a little bit. So t squared over 2 arctan of t minus, this is going to become, let's pull out the 1/2 so we don't have to deal with it right now because we got plenty going on, t squared over 1 plus t squared dt. This is not necessarily a trivial integral, especially as written. It's not a u sub. Might be able to try integration by parts on it. But we can actually simplify this thing. Anytime we have a rational expression where the lead exponent, or the lead terms have the same exponent, or they have the same degree in the numerator and denominator, we're going to use polynomial division to simplify this thing. Basically, remember, a fraction is like division. This is like saying t squared divided by 1 plus t squared. So over here I'm going to do a little bit of work. And I'm going to divide t squared by 1 plus, well, let's write it as t squared plus 1 just to make the division a little easier. So I want to multiply by whatever I need to get this to cancel out. Well, if I multiply by 1, I get t squared plus 1 here, and I subtract going down. This is like plus 0. So this gives me 0 minus 1. Now, with our remainder theorem, we have a remainder of minus 1. And what this tells us is that t squared over t squared plus 1 is equal to 1 minus 1 over t squared plus 1. Now, if you're not convinced of this, find a common denominator and add these back together. But that comes from doing this polynomial division. So we got the 1, that's where this 1 came from. And then our remainder theorem says we take the remainder over the divisor, and that makes them equal. It's just like doing a mixed fraction. So what that's going to allow me to do is rewrite that integral that we still need to solve. So we have t squared arctan of t minus 1/2, and now we're going to write this as the integral of 1 minus 1 over t squared plus 1 dt. Now this is an integral we can do piece by piece. So the t squared over 2 arctan of t is already done. So minus 1/2. The antiderivative of 1 is just t, and the antiderivative of 1 over t squared plus 1, well, we know that that's arctan of t. And then we have our plus c at the end, starting to run into our scratch work there. Last thing I'll do is I'll distribute that 1/2 just to see if anything will simplify any further, although in this one it really won't. You could factor out an arctan if you wanted to, but I'm not going to worry about that for this problem. T over 2 from this, and that we got a negative times a negative, so plus 1/2 arctan of t plus c, and there's our antiderivative.